next presentation is by Oyama, and it's on mechanism of ethanol oxidation in support of molybdenum oxides. It's probed by in situ laser Raman spectroscopy.
There's a small misspelling in the title. I'll be talking about ethanol oxidation, not methanol.
Small miss.
But it's a very great pleasure to be here to participate in this symposium honoring C.O. Bennett, and I'm very thankful to Kurt and Steve for organizing this very nice gathering. I'll be talking to you about...
Maybe the house lights down, I'm sure.
Thanks.
Is this better?
Yeah.
Is it a combination? Okay.
Thanks. I want to talk to you about the mechanism of ethanol oxidation and moly oxide. And in particular, I want to focus on the observation of intermediates with laser Raman spectroscopy. I will talk to you about the observation of true and spectator intermediates during the reaction. Of course, the subject of alcohol oxidation was studied in great depth by C.O., and I want to touch on some of his work in this area as well. And there's been also prior work on the observation of adsorbed intermediates during reaction. And here is a partial listing of a number of systems that have been studied. It's generally difficult to observe intermediates at reaction conditions. I want to note here, though, reference 4 on the CO hydrogen reaction on rhodium, which was studied by CO, and where he observed the presence of spectators during the reaction. What I want to show you today is that in the oxidation of ethanol and moly oxide, there are two different intermediates that are formed, depending on the oxygen functionality with which the ethanol reacts. This reaction with terminal oxygen bonds, there is the formation of a simple ethoxide, which decomposes via an alpha hydride elimination, alpha to the oxygen, to form acetaldehyde. When ethanol reacts with bridging moly groups, another type of ethoxide is formed. And this tends to decompose via a beta hydride elimination to form ethylene. But this reaction occurs only at higher temperatures, higher than the reactions in which acetaldehyde is produced. And in fact, at those conditions, this group is a spectator on the surface, as I will show you. Now, this work is not new. CO himself studied alcohol oxidation, in particular methanol oxidation, on moly oxide, and suggested, based on in situ infrared work, that there were a number of different ethoxide species. When ethoxide adsorbed on the vacancy of the prior moly oxygen terminal group, an ethoxide species was observed. Ethanol could also interact with a bridging oxygen group, or the vacancy drop, to form this methoxide group. And methanol could also add across a double bond to form another form of methoxide. Now, in our studies, we cannot distinguish between forms A and C, but we can distinguish between forms A and C and B. And I cite here the work, and Raoul also was involved in this work. But CO is not known only for his work on alcohol and intermediates, and also on transient work. He's also, it turns out, an excellent cook. And you can see that I'm a bit full there. This picture was taken last year in his Paris apartment. The work that I will describe was carried out in an in situ Raman cell. The sample was in the form of a wafer, which is supported on a rotating rod. The light from an incident laser was collected, filtered, and then passed on to a monochromator. The geometry of this setup was optimized. It was essentially, as shown here, was a minimal number of optical elements. The filter that was employed is a new type of interference filter, and it's extremely good and efficient for removing the Rayleigh light. As you will see, this allows us to take very high sensitivity Raman spectra during reaction. The system that I will talk about is moly oxide supported on different supports, silica, alumina, and titanium, and depending on the support, different forms of the catalyst are observed. With a silica support, the interaction of moly oxide with silica is low, and small crystallites are formed. They have the structure shown here, and these crystallites have both terminal oxygen groups and also bridging groups. So both types of functionalities are found in the crystallites. On alumina and titanium, the loadings that we studied, the moly oxide interacts strongly with the support, spreads out, and mostly monolayer type structures are formed with atomically dispersed moly on the surface. And with these, there are only moly-oxygen double bond functionalities. There are no moly-oxygen-moly bridging bonds. So this provides a very good system for investigating the effect of structure on the reaction. Here are the Raman spectra of the supported oxide samples in the absence of reaction. On top is the silica supported sample. We see a sharp peak at 984 due to the moly-oxygen double bond. A small feature at 819, which however is reproducible and distinct, which is associated with moly-oxygen-moly bridging groups. And there are a couple of bands due to silica. The spectra here we're taking in an oxygen atmosphere, so we see oxygen because of its excess in the cell. In the case of the alumina-supported moly, we see a single sharp peak due to, again, a moly-oxygen double bond. There are some low wave number features which are associated with interaction of moly with the support, but there are no moly-oxygen-moly features here. In the case of the moly and titanium, again, we see the moly-oxygen double bond, 1,000 wave numbers in this case, and at lower wave numbers, bands due to titanium. And again, here there are no moly-oxygen-moly features. So only the silica has this moly-oxygen-moly feature. We characterize the samples with oxygen chemisorption. This is a summary of the results. I'm plotting here oxygen uptake versus the moly oxide concentration in the samples. The dashed line corresponds to a stoichiometry of 1 oxygen atom per moly atom. These chemisorptions were done after pre-reducing the samples at different temperatures for each particular sample. The titanium approaches the dashed curve more closely than the alumina and the silica. This is consistent with the greater dispersion of the moly oxide and the titanium. The moly oxide and the silica is the poorest dispersed. This is where we observe the crystallites. And only at the lowest loadings do all the samples approach the dashed line. Now, this measurement of the oxygen uptake is important because it allows us to calculate turnover rates based on metal sites as titrated by oxygen chemisorption. Here are the results of ethanol oxidation, in this case on moly on alumina. The conversion, indicated by the crosses, increases with temperature as expected. The main product is acetaldehyde. There is some diethyl ether because of the alumina support, but only at the highest temperatures is ethylene and some COX formed. The main product is acetaldehyde. We obtain data like this for the silica and the titania supports, and a summary is shown in the next slide in the form of an Arrhenius plot. And here I'm plotting turnover rate versus inverse temperature. And you see that the titania supported moly oxide is more active than the alumina supported catalyst, which is more active than the silica supported catalyst. The activation energies are all similar. I will not go into the origin of that in this talk. However, there is a substantial difference, about 2 orders of magnitude, between the different supports, and it's not due to a dispersion effect because we are reporting rates based on surface moly atoms. Similar results have been obtained in the case of methanol oxidation, identical results actually. It's the same observation of equal activation energies. In order to investigate the mechanism of the reaction, we did isotopic substitution experiments on silica, alumina, and titania catalysts. Again, here I'm showing the ratio of rates of unsubstituted and substituted ethanol molecules. Let's look at the first column. We're substituting in the hydroxyl position, and the ratio of rates is close to unity, except perhaps for this sample in alumina. But for the catalyst, it seems to be close to unity. This is consistent with equilibrated ethanol absorption to form an ethoxide species, very similar to what is found for methanol oxidation. Now, when we substitute in the methyl position, the ratio of rates increases. It's a possible exception of this sample, but there's a general trend towards increase, and this is consistent with CH bond breaking being rate determining in the reaction. And similarly, when we substitute in the methylene position, there's a further increase in the ratio of rates, again suggesting that CH bond breaking is rate determining. So we have a mechanism consisting of an equilibrated absorption of ethanol to form an ethoxide species, and then a rate determining CH bond breaking, very similar to what is found for methanol oxidation. The small deviation from unity, the positive deviation, is consistent with an equilibrium isotope effect. So the mechanism that comes about that can be deduced from those results is, as I stated, information of the ethoxide species, and then the rate determining the composition of the ethoxide to form an alpha hydride elimination acetaldehyde, beta hydride elimination ethylene, and yet a bimolecular combination diethyl ether. We have measured the kinetics of the reaction. They are shown here. The order is slightly less than 1 for ethanol, slightly negative for water vapor, slightly positive for oxygen. And it matches very nicely with one adjustable parameter, a theoretical rate expression we derived on the basis of a non-uniform surface. But I will come to that towards the end. Let me go on to the laser Raman results. This is a busy slide, and I'll go slowly over it. There's a lot of information here, and maybe I'll turn off many slides at this point, although people are going to fall asleep.
Awesome.
The left panel, and can we adjust the focus a little bit?
You see what you're doing right there.
Okay. The left panel it shows the low wave number region. The right panel shows the high wave number region in the spectrum. The top left panel shows the spectrum of the catalyst alone without any reactant. And I've shown you this before. You can see the main peak here at 984 due to moly oxygen terminally bonded. And then a feature at 819 due to the bridging oxygen, and some other features due to silica, here, here, and there. On absorption of ethanol, shown in the middle panel, figure, there is a substantial change in the spectrum of the catalyst, with the appearance of a large number of bands, which can be assigned with correspondence corresponds to the spectrum of liquid ethanol shown at the bottom. We can assign all the bands. They are due to deformation, wagging bands, twisting bands, rocking bands of the methylene methyl group. What is conspicuously absent from the adsorbed ethanol spectrum is this sharp band at 878 wave numbers, which is due to the skeletal vibration, CCO skeletal vibration of ethanol. This is completely absent. Instead, there's a new feature at 1030 wave numbers. It turns out that there have been recent ab initio calculations of ethoxide adsorbed on moly, and this spectrum matches that reported in the ab initio results very closely. There is the predicted complete disappearance of the skeletal vibration and its shift and diminution of intensity at the 1030 position. So those results are strongly supportive of an adsorbed ethoxide species being involved in the reaction here. Let me go over to the right panel. For the plain catalyst, without adsorbate, there's no signal in this region. When we absorb ethanol, we get peaks that are due to the stretching and symmetric and asymmetric stretching vibrations of the CH bonds in methyl and methylene. And those are shown very clearly here for the liquid ethanol. There is one major difference, though, between the liquid ethanol and the adsorbed ethoxide, and that is that for the adsorbed ethoxide, the two peaks at low wave numbers here, 2872 and 2892, are split. There are two peaks here, whereas there's only one peak for the liquid ethanol case. This is consistent with the existence of two different types of ethoxide groups, one associated with each one of those peaks. If you look closely at all the bands that correspond to the methylene groups, you will note that they are also split. Right there, and this again is consistent with two different ethoxide species being present. Next slide, please, and I guess we'll turn on the lights and see how many people are still awake. This slide shows all the vibrational frequencies that were observed. They have been completely assigned to these in correspondence to the ab initio results of Udall et al. This is just to show you that we have assigned all the peaks. Next slide, please. For silica, as I just showed you, there are those two bands at 2872 and 2892 associated with the two different ethoxide species. In fact, they're associated with the spectator and the real intermediate. For the alumina-supported sample, though, there's only one band at 2872, and for the titanium-supported sample, there's only one band at 2872. And if you recall, in these samples, we only had moly-oxygen double bonds. So this leads us to conclude that the ethoxide species that is associated with the 2872 band is one that is interacting with the moly-oxygen double bond in these structures. And the other one, at 2892, is interacting with the moly-oxygen-moly bridging bonds. We can deconvolute the components in that high wave number region of the CH stretch, and therefore get quantitative information about the relative abundances of the spectator and the real intermediate during the reaction. And if we plot the coverage of the intermediate as a function of temperature, we note a decrease like this with temperature. And I'm not showing it here, but if you look at the intensity of the moly-oxygen double bond, we see a corresponding increase. Again, suggesting that the ethoxide, that is a reactive species, is associated with the moly-oxygen double bond. We can measure reaction isotherms during catalytic ethanol oxidation, and we see that the coverage in the reactive species increases with increasing ethanol pressure, as expected for a reaction intermediate. We also see that the coverage increases with decreasing temperature. And this is exactly as you would expect for an absorbed intermediate. I should mention that the coverage here is normalized to the highest intensity signal obtained at the lowest temperature and the highest ethanol partial pressure. This is where saturation and adsorption is found. And that definition of the coverage agrees very well with the coverage from oxygen chemisorption. So we're measuring the same sites there. Now, what about the spectator? The spectator, whose concentration we can deduce from the deconvolution, shows almost no dependence on the ethanol partial pressure at these reaction conditions. So we conclude that it is an unreacted species, just present on the surface, but not actively participating in the reaction. Here are plots of the rate now versus coverage at different temperatures. If you take any two of these plots, you will see that the rate increases with temperature. This is expected. If you take two of these, you will see that, if you take any one of these, you will see that the rate increases with coverage, and that is expected. And if you take all three, you will see that the coverage increases with decreasing temperature. And again, this is exactly what is expected for a reactive intermediate. Now, if you take vertical slices at constant coverage, you can obtain rates at different temperatures at constant coverage, and that allows you to calculate activation energies as a function of the coverage. So we take vertical slices, keeping constant coverage, get the rates, plot the log of the rate versus 1 over t, get the activation energy, and plot the activation energy versus coverage, and we see that there is a dependence of the activation energy with coverage. This indicates that the surface is a non-uniform surface, and it justifies our employment of non-uniform surface kinetics. And we have actually done that, and I show you here the results summarized. It turns out that a good fit of this sequence that I showed you earlier, the equilibrium absorption of ethanol and then the rate determinant decomposition, can give, using the Fromkin-Chomkin methodology, an expression for the coverage, which depends on the natural log of the ethanol partial pressure. We have gotten all the parameters. The F value represents the breadth of the non-uniformity, which is pretty broad here. The K10 is the reference adsorption equilibrium constant at zero coverage. The rate constant is similarly given by this expression here, where alpha is the transfer coefficient, again determinable from the linear dependence of the rate on the coverage. Now, as CO might say, the ultimate proof of a mechanism cannot be obtained just simply from steady state measurements. You must carry out a transient experiment, and here's one such experiment. We are starting at time 0 with the reaction at steady state, and we're cutting off at that point the ethanol in the gas phase. And we are monitoring the decrease in the coverage and the decrease in the rate of acetaldehyde formation. As you can see, the two track each other pretty well within the limits of uncertainty in this experiment. The correspondence between the two curves indicates that those two are associated and confirms the assumptions of our reaction model that the ethoxide is the actual reaction intermediate. Note that the coverage does not go down all the way to 0. It goes down to a particular level here, which corresponds to the coverage of the spectator, which does not change in this experiment. The spectator coverage is about 3 times higher than the actual intermediate coverage. So this teaches another lesson, and that is that It's very dangerous to do in situ measurements without doing some kind of experiment to prove that what you are observing is an actual reaction intermediate. Just observing an intermediate during reaction is not good enough to show that it's a reaction intermediate. So, to conclude, ethanol adsorbs through an equilibrated step to form ethoxide intermediates. The rate-determining step is alpha hydrogen abstraction from the ethoxide group. The same mechanism occurs on the silica, alumina, and titania supported sample. We saw that from the isotope effects. The kinetics are well described by Chomsky's theory of rates of non-uniform surfaces. And there are two types of adsorbed ethoxy groups. The true reactive intermediate is associated with moly-oxygen terminal bonds, and an unreactive spectator is associated with moly-oxygen-moly bridging groups. And with that, I thank you for your attention, and I'd like to answer questions.
Couple questions in here. We've got one right here.
How do you get the isotope effect when you put deuterium in the methyl position?
In the
When
methyl
you,
position.
yeah, you have CD3. For
We
dehydrate.
just measure the rate of the consumption of the ethanol in both cases. It's just looking at the ethanol, just looking at the conversion of the ethanol. Carlo?
Yeah, you observed the rigid bonding oxygen only in the case of silica.
Silica, yes.
And then on alumina and titanium you didn't. And up to what loading?
Up to about 5 to 9%.
In either case, alumina or titanium?
Yes, on titania there is more dispersion, but the surface area is slightly lower. So between 5 and 9%. I don't remember exactly.
Did you carry out any of the kinetics for those loads?
At the high loadings, no, not on the alumina and titanium, none of those samples.
Okay, that was related to the kinetics. First order on the actual intermediate, right? Right?
Yes, first order absorbed
For acetaldehyde production.
4 acetaldehyde. What about
For the heat.
for the ether? That was only observed on the alumina sample, and we did not do the full kinetics on the alumina sample.
Yeah, I wanted to follow up that question a little bit. Of course, you've got various ways of making catalysts and so forth, but on the typical 8% impregnated catalyst, after calcining at about 500 degrees C, there's a considerable body of evidence that points to clusters, clusters with open alumina surface in between. And it's, I've always supposed that those contain bridging oxygens because the precursor, the paramolybdate ion, has bridging oxygens in it. That's all, just a comment. I don't.
I have not done the measurements myself, but there have been very good studies by Israel Watts on exactly the same system at similar loadings, and he reports isolated species by a number of techniques, including NEXAPS and Raman spectroscopy. So I think I will go with that. I'm pretty sure that they are isolated molybdenum terminal groups.
Awesome.
Last question here, but
Coming from here, that's actually from hydrated and dehydrated samples. Dehydrated ones and isolated ones, hydrated ones are the cluster ones. Now the question, am I correct in suggesting that there's a wonderful occurrence now in the literature of opposite action to occur? Ethanol onto the terminal oxygens, metal oxygen support bond being one
speak to that from the experimental results. It's definitely a possibility.
Isotope insertion reactions, where he's putting OAP in the tank, and OAP only goes to the metal oxygen support one, not to the thermal one, which is not inconsistent with what you're saying.
You're referring to reducing the molyoxygen species and then deoxidizing
Switch
with...
over to oxygen 18, then you find the oxygen 18 exclusively incorporates into the molecular oxygen support one, not the moly oxygen return one.
After reduction?
During reaction.
During reaction. I'm not aware of those results, but yeah, that would be evidence for participation.
Because everything you said is sort of consistent with that, as long as you have still the site for the epoxy to absorb on the terminal place where everybody's happy.
Very true.
You're not addressing what happens subsequently.
Exactly.
Thank the speaker. We have to keep moving.